In this lesson, we're going to talk about approximation of the binomial distribution by a Poisson distribution. So it should be evident to us from the principles of the Poisson process that the Poisson is related to the binomial. And in the case of the binomial, if n is quite large and p is small, the conditions begin to simulate the continuous space or time implications of the Poisson process. The independence among Bernoulli trials in the binomial case is consistent with the principle 2 of the Poisson process. So allowing p to be close to 0 relates to principle 3 of the Poisson process. So if p is small, so if p approaches 0 and n is large, so n is approaching infinity, so n is getting large and p is small, the Poisson distribution can be used with mu equal np to approximate binomial probabilities. If p is close to 1, we can use the Poisson distribution to approximate the binomial probabilities by interchanging what we have defined as a success and a failure. If we just flip them, then now p becomes close to 0. So let's let x be a binomial random variable. So x is a binomial random variable with probability distribution bx np. Then is going to infinity. This remains constant. So let's look at an example. Okay, so if we look at this example, we have glass products are made when they're manufactured. Defects and bubbles can occur, and that would be at a rate of 1 in 1,000 is equal to a defect. So what's the probability that a random sample of 8,000 will yield fewer than 7 defects? So when we look at this experiment, n is 8,000, n is equal to 8,000, so that's large. And we look at p is equal to 0.001, and that's small, that is approaching 0. So since it's close to 0 and n is large, we're going to approximate this binomial using the Poisson distribution. So our mu, in this case, so mu is equal to n times p for our binomial, and that is equal to 8. So we will use 8 as our mu, which is equivalent to our lambda t. So we're going to our table, our Poisson table, where there is column 8.00, and we're looking for what is the probability that it's yielding fewer than 7 defects. So fewer than 7 would mean, this means at most 6. So this is quite simple to go to the Poisson table, go to 6, where r equals 6, under column 8, and that is 0.3134. And again, that's column 8, row 6. And the answer is a probability of 0.3134. If we tried to do this via the binomial, our probability is really small, our n is very large. We would not be able to use the tables to compute the answer, and we would have to do the calculation, which is doable. So we would do it from 0 to 6, and we'd have to sum those. So obviously much simpler to estimate this with a Poisson table than to do the manual computations.